Hi, welcome. This is a presentation of the paper towards a better understanding of label smoothing in information translation. My name is Yingbo Gao, or Ringo for short. I'm a third-year PhD student under the supervision of Professor Hermann Ney at RWTH Aachen University in Germany. So here's the agenda. First, I'll introduce the topic and describe our motivation. Second, I'll talk about the criterion in our solutions. Third, I'll go over the experiments and explain how we approach a good recipe to successfully apply label smoothing in MT. Actually, during the course of that, we found a training and testing mismatch problem. So in step number 4, I'll describe search and scoring and our intuitions of why. And finally, conclusion and outlook. So first, what is label smoothing? Label smoothing penalizes overconfident model output. Generally speaking, it leads to worse training perplexity, but better testing performance. In the transformer architecture, label smoothing is actually included as a default regularization method. Why do we want to study label smoothing? Well, smoothing is a never-ending story to model uncertainties in data. Even nowadays, we sometimes even have over 100 gigabytes of raw text, but still it's impossible to see all word combinations in even such a large data set. So that means unseen events will always be there, and smoothing as a topic will always be relevant. Label smoothing itself is a very simple idea which works incredibly well in practice. So in this talk, we want to understand it better, and I will try to answer 3 questions. First, can we solve the training problem analytically? Second, what's the best practical recipe to apply label smoothing? And third, is there anything we have missed before? Before I show you the derivations and the theory, I would like you to take a moment and rethink about the prior distribution. Originally, we have a one-hot target distribution, so 1 at the target word v0 and 0 elsewhere. What label smoothing is doing, essentially, is we're discounting some probability mass m and redistribute uniformly or equally across the whole vocabulary. A natural question to ask ourselves is that the smartest thing to do? Or do we know anything about the unseen events? Take the simple sentence, I like swimming, for example. Maybe we want to redistribute a bit more probability mass from swimming to words like cooking or reading or any other common hobby, which could make more sense. All right, so this is the standard label smoothing loss. Notice the subscript n here. So essentially it's a local loss. We omit the outer summation over the tokens as well as the average. Looks like a cross entropy. The only difference is that the p log v formation, the p is replaced with a linear interpolation between pv and 1 over v controlled by the linear interpolation weight m. Now people already know that the solution to this problem is simply the linear interpolation again. One can either use the divergence inequality or the Lagrange multiplier method to obtain this. A very closely related method called confidence penalty can be written as follows. Again, local loss. The difference is now we are minusing m prime qv. So notice this is not a proper probability distribution anymore. But nonetheless, we can separate the terms. The first term will be cross entropy, and the second term will be information entropy. And we know information entropy is a measure of the uncertainty, and it takes its maximum at the uniform distribution, and we want to minimize the whole thing. So qualitatively, people know that training with this is basically penalizing divergence from the uniform prior at the same time. But in this work, in our work, we can analytically show and solve the optimization problem. On a side note, this is not a probability distribution, but if you really want it to be, what you could do is you can take away the minimum and normalize over the vocabulary or apply the softmax. All right, so we want to solve this. Divergence inequality seems very hard to directly apply, so we use the Lagrange multiplier method and calculate the gradient. Once the gradient shows up, we'll see this is essentially a transcendental equation when we set it to 0 because we have a q log q showing up. But since we know that the Lambert W function gives the inverse relation to x e to the x, so when we replace the variables, we can use the Lambert W to represent the final optimum q. So that's exactly what we did, and this is the optimum. What this gives is basically a nonlinear relationship between q and p, controlled by the hyperparameter m prime, and lambda being the Lagrange multiplier in this case. So when we plug in a realistic vocabulary size like 32,000 when we apply BPE to this formula, we can numerically plot the trends. So the x-axis will be the smoothing strength of m or m prime for standard or confidence penalty, and the y-axis will be the optimum solution. For the left side is target words, for the right side is non-target words, and we'll see it drops from 1 to 0 for target words and increases from 0 to the uniform distribution for non-target words. The only difference between these two criterion is just the curvature here. So it's very nice. We have better understanding now. We could write a more general formula. So we make two modifications. One is that we consider the outer summation over the target tokens and split them into two sets, one set for smoothing, one set for no smoothing. And also the second modification is here. Recall previously we have 1 over here, 1 over v here. Now replace it with an arbitrary distribution that could depend on v or qv. In terms of how to choose, there are two simple ideas. Either we can choose at random, or we can choose by decreasing order of the entropy of the prior distribution. So the motivation here is basically words like dog and cat we're most uncertain about. We should probably prioritize on those words to smooth. And a final note for this formula is that the m parameter is still treated as a hyperparameter parameter in our case, so essentially a number, but you could make it depend on the position, for example, or more. So something like an adaptive smoothing strength. We leave it for future work. All right, so the experimental setup is quite standard. We work on 6 IWST language pairs and 1 WMT language pair. We apply joint PPE of source and target, 10K and 32K merge operations for IWST and WMT, respectively. In terms of pre-processing, scoring, architecture, training, scheduling, and so on, it's quite standard. We use the FAIRSEC toolkit. Our experiment philosophy is basically that we want to do a big grid search over 3 interesting hyperparameters, which are which tokens to smooth, how much smoothing strength, and which smoothing prior. And since searching over the whole cube is probably too much, we only take meaningful slices or meaningful lines from this cube. So the first question, which tokens to smooth? Now, what's plotted here is IWST, German English, M is 0.1 with the LM helper. Actually, we can also use unigram or uniform, other kinds of priors. We also did the experiments and the trend look very similar. So first thing you should notice is that when pi is 0, so smoothing none of the tokens, or when pi is 1, smoothing all of the tokens, the two methods meet at the same point. This is actually a very nice sanity check that our implementation is more or less correct because the two methods only differ in how they choose a percentage of tokens. When we smooth none or all, it should be exactly the same. And both curves follow an uphill trend, and this is quite consistent across our experiments. So we answer the question by saying smoothing all token is probably better. All right, the second question, how much smoothing strength? So we work on IWST language pairs again. To the left is smoothing with uniform prior. To the right is smoothing with unigram prior. Turns out when you smooth with m equals to 1, you're basically penalizing your model to output a uniform distribution from this plot. And a nice sanity check is because perplexity can be thought of as effective vocabulary size. So this model trained with this criterion has to give a perplexity at least in the order of the vocabulary size, which is exactly what we observe. So again, that's a very nice sanity check. And also, if you look at this plot, there is a huge plateau or leveling over the domain of M, which means the neural networks are very good at picking out effective training signals from the noise, which is the uniform prior in this case. And also, if you consider a typical multitask learning setup where we have the original loss L1 and plus lambda L2, which is some regularization loss, this gives a hint of why lambda could be hard to tune, because the sensitive regions to such parameters could be very, very small compared to the whole region. And finally, we did many experiments, and for us, m equals to 3 is a quite consistent choice for the smoothing strength. And finally, which smoothing prior? Now, we could do uniform, unigram, or even more complicated models like a language model at the target side or a translation model doing forward translation, all of which could give us prior distribution. So in these two plots, left side is LM, right side is MT when we smooth with either LM or MT. Now the expectation should be as the helper model perplexity gets worse, the blue should also get worse. So downhill trend. To the left side is loosely the case, but to the right side is really not the case. So we were stumbled and we checked our training and testing log. Turns out the development step perplexities do improve. It's just the test blue scores that are not. So that signals a training and testing mismatch. But anyways, to answer this question, for us, the unigram prior works quite well. All right, so before looking at the mismatch problem in more detail, this is the summary of our best recipe. So if you do no smoothing, that's row number 1. If you apply transformer smoothing, label smoothing, that's row number 2. And if you apply our best recipe, that would be row number 3. And you see across the board, we have about 0.5 blue score improvement over the transformer baseline, which is nice to have. All right, so we mentioned a mismatch problem. First thing we checked was search. Does search look normal? So if we plot the blue score versus the beam size, for uniform, unigram, and no smoothing, these 3 curves all look normal. It increases, plateaus as the beam size gets larger and larger. However, for the purple curve, model smooth with LM helper, this is not what we expect. Our intuition or our explanation is that probably a model smooth with LM helper generates a complex search space where the true target is probably not even in the beam when the beam size gets too large. All right, we want to consider the mismatch a bit deeper. The one set perplexity doesn't agree with test blue. So there are 2 things, dev versus test, perplexity versus blue. So if we scatter 79 convergent models of adipose RT Spanish English, so each data point will be a single system, and we look at test blue versus dev blue, we see a very nice correlation. That means a better dev blue means indicates a better test blue score. So there's no intrinsic data mismatch in our dev and test. But when we plot test blue versus dev perplexity, we see the problem. In the low or bad perplexity region, it follows roughly this red curve. This is exactly how we do the fit, which means, okay, the better the dev perplexity, the better the test blue score. But in the region of low dev perplexity, we see many systems with very, very different test blue scores. And our LM and MT smooth models are among these. So in other words, we can obtain better trained models in terms of dev perplexity, but not necessarily better scoring models in terms of test blue. And I would like to raise a bunch of questions here to make you really think. So do we see this problem often enough? Or is it possible that we have thrown away some really good models simply because the test blue score was not good, and maybe the dev perplexity was actually very good? And what to do? Should we replace dev perplexity, or should we replace blue score? Will be a fair judgment of how good a system is. All right, that's pretty much the representation, and I would like to highlight what we think is important in the end. So first, theoretical solution. Well, we show that confidence penalty is pretty much an extension to standard label smoothing. We generalize the formula and leave adaptive smoothing for further exploration. We tune the hyperparameters and show that if you do smoothing, that's the largest improvement. If you do smoothing very, very well, you can additionally gain some blue score improvement. And then I spent quite some time talking about this training and testing mismatch. To summarize in one sentence is basically, how should we judge a model with a good loss but a bad score? Finally, label smoothing works at the target output side. How about the input side? Can we do something similar? What would be the implications? Actually, we did some work and have a paper published this year at Calling 2020 called Unifying Input and Output Smoothing in Your Machine Translation. If you're interested, please take a look. All right, so much for the talk. Thank you very much for your attention, and I will be very happy to take your questions. Bye.